So today I'm going to be talking about shaders. Shaders are really cool and they're really powerful, and now we can use them on the web with WebGL. So that's basically entirely what this is going to be about. So there are existing sort of websites that you can go to and play with shaders. These are all basically like two-dimensional kind of like what shaders were intended to be used for, well, sort of like what shaders were intended to be used for, like taken to the extreme. People playing with just sort of like live code editors, and you know, like I don't know if I need to go here, but like there's, you know, some really cool stuff going on these websites. If you haven't been to Shader Toy, you owe it yourself to check it out. There's some really like mind-blowing stuff that people are doing. So I'm going to talk about my kind of like addition to this, which is sort of somewhat tangential, but is a Shader Toy nonetheless. So this is, like, you may have seen a diagram like this before. This is sort of like the canonical kind of way that people explain OpenGL rasterization. So you have like a triangle, and then the triangle gets converted into fragments, and those fragments are then rendered. So each one of those fragments will go through a what's called a fragment shader. So you have when you render anything in OpenGL, you have a vertex shader and a fragment shader. The vertex shader will tell the GPU where to put the points on screen, and then the fragment shader tells it for every pixel or fragment that triangle is covering, what color should it be, or like should it even be a color? Should it even exist? Should it render anything there? So that's kind of like the like super high level like overview, and sort of like the novel thing about the like shader editor that I'm going to be talking about is that instead of rendering those pixels directly to the screen, it will render them to a frame buffer, and then use that frame buffer to draw points on screen. So you could think of each pixel as like a point in 3D space. So instead of RGB, you think of that of the RGB colors as like an XYZ position, and then the other thing that you add to this is that you then feed back the image. So you have a position and you have a previous position, and then you render to you render to a new texture, sampling the old texture, and then switch them so that you can sort of like propagate a value over time. This is called a ping pong frame buffer, ping pong texture, or something like that. So with those two things, you can have awesomeness. And yeah, so I will show you. Let's see. I should start a timer here so I don't go too fast. So I'll show you some examples of this in action. So I wrote like a couple years ago. I wrote this tool. It's called, or tool or toy. It's called Yet Another Shader Editor, because there are a lot of them, and this is yet another one. And it looks like this. So hopefully. So we have the result and the shader on the left here. So this is sort of like one of the more complex shaders. If you were to just go there, without without anything. If I was to go here and show the navigation, you would see this, which is a much simpler shader. So basically, we're just selling it. We're just telling it what the position of the particle should be, and then like the W component is used as the brightness of the particle. So we're just setting the W component to be the Z. So this is like a really simple thing that, like one of the more simple simple examples. This one is using the feedback that I was talking about earlier to do like a sort of particle like chain simulation. So each particle looks at its neighboring particles and then sort of propagates it iterates its position over time. I can show you some that are a little bit more sort of that are iterative in a different way. So this is like an IFS fractal, like iterative, I think iterative function system fractal. And this is what the code looks like. It's not very long. There's another one that uses uses velocity. So this is like a sort of anemone-like kind of creature. Let's see. There's another one. So there's another one. This is a three-dimensional knot. This is the source code. It's not that much. So this is kind of it's like creating these shader toys allows you to be really expressive in a small amount of code, and your sort of your code is propagated over like sort of like in this case thousands of points. So just doing one thing slightly differently for every point gets you like an interesting or somewhat interesting looking image. So I'll just show a few more. So this is an example of using a noise function. This is actually one of the more sort of more complicated shaders. And then recently, I've been getting into using distance fields to control the movement of particles. So a distance, like a signed distance field, is basically like a function into which you can look up from a point, and it will tell you which like how far away you are from an object. And if you're inside of that object, it'll give you a negative value. So in this case, we're looking up into a sort of into a distance field filled with spheres and cubes, and each particle is sort of looking into that field and sampling in multiple directions to get the gradient of the field, and then it's moving toward the sort of it's moving toward the zero like value of that field. So I guess you might call it like the limit of the function or something like that. Like basically like the boundary between the negative values and the positive values. And you can take that a little bit further and do something like this. So this is like a Menger cube being sampled into by thousands of particles. And if I show you the code, it's a reasonable amount of code for these more complex things. Let's see. Let's show a couple more. So this one is a planet. Takes a minute for the sun to come around. And then this is a exploding planet. So what I thought what we would do is that I would show sort of like I'm working on a new version of this tool. The one that I just showed you is online, and you can find it. Like I'll have a link at the end of the talk. But this is sort of like the new version that I'm building to sort of like simplify the way that you write these programs. So I'll kind of just go through this function and explain like what's happening here. So in order to, this is sort of like a subset of there's a lot of setup involved, or like a sort of minimal amount of setup involved. So in order to simplify it, this is sort of like the API that I'm providing. So you have a function, you define a function called iter. It takes a point, which has a position, and the position has an x, y, z, and w component. The point also has a color, which has like RGB A. It also has a previous position, so point p.prev. And then you basically just set the points, set values on the point, and those will be rendered every time the function is called. So let's look at some code, or some more code, some different code, some live code. So let's see. Can people see that all right? It's visible? Okay. So here I have the result of that code that I just showed you. It creates a sine wave. So it's setting the y position to be the sine of the time plus t, which is the index of the point divided by the count. So like a 0 to 1 value, or 0 to almost 1, times tau, which is just pi times 2. So we can basically replace this with like any function. Like we can set the color. So if we want it to be red, we can say, there you go, it's red. We can set one of these values to the t value. So we can set this to sine of t plus time. let's see. Let's see, and then I have some cooking show style examples here, just in case. So this is like a like Archimedean spiral. Let's see. So we're setting the position to be tau times 10. We can get a larger spiral, can kind of inspect it. You'll notice that the color is still blue. This is because like the last change that you put into the system is like sort of like it doesn't forget old values, so you don't have to keep setting them if you set them before. Which means if your shader doesn't set a value, it's just going to use the value that it already had. So which means we can do sort of interesting things like we can take this velocity function and we can replace the whole thing with it, and like the system will just continue along the velocity it had from the previous frame. So what this is doing is just saying like the position, the velocity is equal to the position minus the point's previous position, and then it's just adding the velocity to the point's like XYZ position. So super simple, and you can kind of like you can get a bit more advanced than that and start introducing gravity. So only two-dimensional, but still. So it's doing the same thing as before. We're just taking the velocity of the particle, and we're subtracting a little bit from the y component of like the velocity to make it fall down. And then we just say if the y position is less than -1, which is this plane down here, then we should set the y position to basically it just flips the y across the like a line at -1. So if it's 0.5 below -1, or if it's like -1.5, it'll be -0.5 after it's flipped. So you get something like that. Let's see. So I also put in a sort of noise function, which I'm sort of debating whether or not to keep in there, or like the other option would just be to let it be user-defined, which is the style that they use on shadertoy.com, which is sort of like something that I really like about that site, is that they kind of don't provide any. It's basically like just a fragment shader, and they don't provide much utility besides the things that you would expect from a fragment shader, like what's the position of the pixel, like what's I guess like what the time is, like stuff like that. Right. So this is a noise function. We can change the size. We can change the sort of resolution of the noise function. Let's see. Let's see. So then there's something else you can do with sort of like similar to what I was doing before, which is taking the gradient of a function at a given point. So what this is doing is it's taking it's sampling into the noise like 4 times, and it's getting that gradient out as a 3-dimensional vector, and then it's using that as the color of the particle. So let's see. And you can kind of use this as like a pseudo lighting. So let's see if I can kind of risk doing some live coding here. So if I take the dot product of the normalized gradient and some vec3, let's say, so this is XY coordinates that we're looking at. Z is coming forward, so so we can say normalize vec3 of, we'll say it's to the top center, something like that. And then we have to create a vec3 out of this since it's just a float. GLSL is very picky about what types you use with it. So so it's a little bit janky because of the precision of the noise function, but you can get the idea. Like this is basically how I was doing lighting in the other examples, like the planet and the cubes and measure cube and that type of stuff is basically just treating the gradient as like a surface normal. And then let's see. Hopefully this one works. This is kind of like a translation of a previous example. And it may not. Oh, there we go. So this should be some sort of fountain. I may have gotten the point a little bit off, but no, maybe if I do, that's it. So this should be -1 or just 0 or just 1. So I'm taking that, and so this tool still needs a little bit of work. This is kind of like a prototype that I'm showing you, but basically that's that is the tool. So my goal with this was just to try to get people to play with this stuff a little bit more. It's pretty fun. So if you want to check out the new version, it is the top URL. There's no live version yet because it's sort of like only semi-working. The old version is on the bottom, which is the one that I showed all the demos in and is pretty fully functional, but one doesn't have color and yeah, slightly more old school. But yeah, that's basically it. So thank you.